Okay, so what it means that steady state solution means that this solution is achieved after infinite amount of time, like when your circuit reaches its in its stable state. Okay, and the transient solution means that it means that your circuit is not in the stable state, but it is greater than time equals to 0. So it's what you should say is tau, if tau is greater than 0, and then your transient solution is before this solution. Another thing is that you also call this as time constant, and we know that. So by examining this solution, you know that this is a constant and this is a decaying exponential. So what it means, we will learn that what it means to have the decaying exponential in our, what you should say, solution. So if we plot just this here, we will come to know that if this is our plot and this is k2e minus t by tau, so this decaying exponential will start from here and here if it is time axis. If this is a time axis. What this value is, that you know that if t is equals to 0, e minus 0 is equals to 1, and your k2 e minus t by tau is equals to k2. That's why this point is k2. And then you started from here as your time is increasing. So this said that if we plot this, this is tau. This is 2 tau. This is 3 tau, 4 tau, and 5 tau. So what this means that what is 1 tau? So they said that at 1 tau, you actually lost 63.2% of the original value. So it will be K2 minus 0.632 K2, which will make it this one, 0.368 K2. So this will be 0.368 K2. So at 1 tau, your value of decaying exponential will be 0.368 K2. Similarly, for each tau, the drop will be approximately 0.632 K2. Until and unless when you reach 5 tau, they said that xc of t, which is the natural response, will be 0.0067 K2, which will be very, very small, less than 1% of value of K2. So it means that as time crosses, your transient settles down to its minimum value. Now, as our whole equation is just not that, in our whole equation, so one thing I think you remember, that this is xp of t plus xc of t, where this was natural response, and this was forced response, right? So we are right now talking about a natural response. So one more thing we want to know that, so we know that this is a decaying exponential, right? And decaying exponential means that it settles down as the time passes. But we also want to know what will happen if we change the value of tau. So from the formula, you know that this is E minus T by tau, where this is in the denominator. So if tau increases, the decaying exponential will decrease. Okay, what it means, let's see. So tau increase makes slope decrease, or you can say slow response you will see. Similarly, if tau decrease, you will see slope increase or fast response. What it means, let's see. Let's say you have tau is equals to 4 seconds, and then what will happen? And you have tau is equal to 0.5 seconds. What will be the difference between two graphs? That tau is equals to 4 seconds will be something like that, and tau is equals to 0.5 seconds will be something like that, which means that this response will be slow for larger tau, and response will be fast for smaller tau, which means that for smaller tau, your circuit will settle down quickly, right? Am I clear about that?
Yeah.
Okay, so let me put one more thing. So as you know that our equation was this. So we just plotted this. So if we plot the whole thing, what it means. So for the plot of whole thing, it means that for t is equals to 0, what will be the value here? X of t will be what? X of t will be k1 plus k2, right? Previously, when we were just plotting this, at t is equals to 0, x of t was k2. But if we are plotting both of them, x of t was k1 plus k2. Similarly, for t is equals to infinity, x of t will be what? K1 plus k2 e raised to power minus infinity. So it will be only k1. So it means that at t is equals to 0, it will be k1 plus k2. At t is equals to infinity, it will be only k1 because this term will be 0. So if we plot this thing here, this is our t is equals to 0. And so I am trying to plot it here. So this is k1. And this is k1 plus k2. So my graph will start from here, k1 plus k2, and it will be decaying exponential, but the values are different because we are just taking the whole thing now. So it reaches at k1, and again, its value should be dropped 63% at one tau. So it means that at tau, it should be at tau is equals to, or t is equals to tau, it will be what you should say, k1 plus k2 e raised to power minus 1, right? Which will make it k1 plus 0.368 k2. Sounds good?
Yeah.
And t is equals to infinity. This is maybe, let's say t is equals to infinity, or after a long time, it reaches at its value k1. So that's how we talk about that, how the exponential function will react for in the transient state and in the what you should say, steady state. Okay, now we will try to solve our problem with that. Okay, so this is we will say that this is state variable approach. What it means, that in this technique, we will write the equation for voltage across the capacitor and equation for current through the inductor. So this thing is important, that we will write equation for voltage across the capacitor and equation for current through the inductor. What it means, we will just know right now. And we also know that VC, that is voltage across capacitor, and current across inductor, current through inductor, they do not change instantaneously, right? What it means, that they do not change instantaneously. They both take time to develop the voltage across the capacitor or current through inductor. For the capacitor, we see that when we connect the voltage source, it takes time to reach its maximum. Similarly, for current, it takes time to pass through that. So that's why we will take care of this scenario. So let's start doing this thing here. Okay, so I am doing an example. In which I am having a circuit So in this example, we have two elements. One is a resistor and the other is capacitor. So we need to take care of both of these elements. So our step one to solve this equation will be, or the question will be, we are given that at time t is equals to 0, switch close. Okay, so we want to know that what will happen at a time t is greater than 0. Okay, so define steady state solution for t is less than 0. You need to know what is happening for t is less than 0. Okay, so if there is a charge across there, across the capacitor before, or something like that. So I think there is no charge. Capacitor was initially uncharged at t is less than 0. Okay, so we are given this thing as well. Now, step number 2 is we will write the KCL equation for t is greater than 0. So t and tau is different, you know. So t is the time and tau is the time constant. So just don't confuse them. So we will write KCL equation for t is greater than 0. And if we think that this is our node, what will be, and for t is greater than 0, you know the switch will close. So the new circuit will become yes. So this is our VS. Okay, so if this is our node, what should be the KCL equation here? First, what should I write? If I consider this resistor in the path, and I'm writing the node voltage here, the KCL equation, what should I write?
I'm a little confused, but is it V of t minus Vs over R?
Yes. So this is yes. What is the confusion about that?
I just didn't know what you were asking for. But
yes. Yes. So that's what I was asking. So this is V of t minus Vs over R. Now, so this is the thing that I have written for this current. Now I have to write what is the current that is passing through the capacitor. And we know, we learned in the last chapter that the current, if we write it through the capacitor, it will be C dV over dt. So that's what I will write here, C dV by dt. And this is equals to 0. Okay. Okay, now looking at this equation, okay, what we will try to do is we will try to make this equation in this form.
I just have a quick question.
Yes, go ahead.
Why would it not be Vs minus Vt over R?
Okay,
like
1 minute. No. So what I'm doing is I am writing the equation for this node, right?
Okay.
And I should also write this V of t here. So when I'm writing the equation for this node, I call it V of t, right? So if I am writing about this node, I will start from here, right?
Okay.
So that's why I said V of t minus Vs over R. you also you are saying that the equation, the current direction is this, right? So if the current direction is opposite, it will automatically come as negative or positive. But right now, because I am considering this node, I will consider it as the central point.
Okay.
Right? So I know that the current is flowing in this direction, but when we are considering some node, we consider it at the central point, or all the other signs falls according to it. Okay. Okay, so what I'm saying is that we know that this is a differential equation. So I want to write it in this form because I know the solution of this form, right? So I will try to convert this equation into this form. Okay. So for that, I think I need to okay. So now you can see that I have this form. Okay. So if you compare my equation to this form, you can see some similarity.
Yeah.
Okay, so if I just write what I'm seeing here is, you can see that in these two forms, x is v of t, a is 1 over rc, and f of t is vs over rc. Okay, and as we know before that a is 1 over tau. So if you see here, a is equals to 1 over tau, or tau is equals to 1 over a. So we can also say that a is equal to 1 over tau, which makes tau is equals to rc. Okay, so if I write the solution of this form, right? That was my solution. And if I write same solution here, that would become right.
Yep.
Am I right about this?
I'm a bit confused on how you got A is equal to 1 over RC. Can you explain that again, please?
Yeah. Okay, let me go back. Okay. So if you see here, just forget about tau right now here. If you just see here, so you are good with this equation?
Yes, yes.
Okay, if you compare this with this. Right, you know that this equation's solution is this, right?
Yeah.
So if you just compare these two, so you know that whatever you will have here would be A, right?
Yes.
So just stick with that, okay? They just said that this A is 1 over tau. They just define it another term. But even if you don't define it, you just keep it as A. If now you compare it with here, this A is equal to 1 by RC, right?
Oh, okay. From the other equation. Okay, thank you.
So they just said that whatever, just to make it easy, they said that let's replace this A is equals to 1 by tau. Okay? But ultimately it will come as this. Sounds good?
Yes, thank you.
Okay, so we got this, right? But what is the problem now? We now know the solution, but the problem is that in this solution, we don't know K1, we don't know K2, and we don't know, we can know RC by knowing the values of R and C, but we don't know, right now, we don't know these things, okay? So what should we do to find them out? First, what I will do, now I know the solution, so I will replace the value of V of t in the differential equation. Okay, so when I will replace it here, it will become d by dt k1 plus k2 e minus t by rc plus k1 plus k2 e minus t by rc is equals to vs by rc. Okay, so now it will become, so if I replaced not by RC, I just replaced by tau, it's the same thing. So I am just writing it as it is. K1 will be 0. K2 will become minus K2 by tau, E minus T by tau. And here it will become as it is, K1 by RC or tau. Replace tau is equals to RC. Okay. K1 by tau, K2 by tau, E minus T by tau is equals to Vs by tau. Okay. What they actually done is that, 1 minute. Before getting it too much confused, I will do what this. So here I will replace it by tau, okay? So I will do this here. It didn't make any difference, but to just keep these two things different. Okay, so this will be tau, so I'm just writing it here. Because I got confused. Okay. Okay, now I will do it again. So this will be K2 by tau, E minus T by tau, plus K1 by RC, plus K2 by RC, E minus T by tau. You know what I did that? Why I did that? Because I want to keep separate this RC and this tau. I just want to keep them separate. Previously, I actually replaced everything by tau, which is not right, because this is tau, and ultimately maybe this will be equal to this, but I want to keep them separate right now. Okay, so I got this equation, and now if I see in this equation, you know that this and this and this are constants, right? So at t is equals to infinity, they will be equal to K1 by RC is equals to Vs by RC. Or if I equate the constant terms and exponential terms, then it will be like that. So this will become K1 is equal to Vs, right? So K1 by RC will be equal to Vs by RC, which will make K1 is equals to Vs, right?
Right.
Okay, so now, okay, K1 is equals to Vs and okay. Now I know I want to find, I know K1. Now I want to find K2. So if I replace K1 as Vs here, Vs plus K2 E minus T by tau, or I can also write Vs plus K2 E minus T by RC, right? Now I have to find K2. To find K2, I will use its initial condition. As I know that according to the initial condition, at t is equals to 0, Vc was 0, right? So if I put t is equals to 0 here in this equation, this equation will become, this will be 0, Vs plus K2 E minus 0, which will become Vs plus K2 is equals to 0. So why I put 0 here? Because if you see this equation, in this equation, I put this thing at 0 at t is equals to 0. Now come back here. So this V of t was actually the voltage across capacitor, right? Which is 0 at t is equals to 0. So that's why this is not Vs. This is not the whole voltage. This is the voltage across capacitor. That's why I did that. So if I just do here, Vs is equals to minus K2 and replace value of K2 in equation of V of t, this will become V of t is equals to Vs minus Vs E minus T by RC. So if you see here, I replace here minus Vs and we are becoming here Vs minus Vs E minus T by RC. Okay. Now, if you plot this voltage here, let's see. So you know at this is t is equals to 0, and this is, let's say, t is equals to infinity. So you know at t is equals to 0, what will be the value here?
0.
0, right? And at t is equals to infinity, what will be the value?
K1.
Yeah, Vs or K1.
Yeah.
Vs, right? Which is K1, right? So it means that as this is also can be written as like this. Right? So this is your final value here. So ultimately, the graph will be something like this, right? And if you see at t is equals to RC or t is equals to tau, at t is equals to RC, it will be Vs 1 minus E minus 1. So it's not 0.368 value, but it is 0.632 Vs, right? Because 1 minus 0.368 will be this. So it means that instead of decreasing, it's a growing exponential. So if this is your RC, this will be your 0.632 Vs. Sounds good? Am I right about this?
Yeah.
Okay. Now, why we are seeing a growing exponential instead of decaying exponential? Because this circuit is not about discharging. This is about charging the capacitor. Okay. When we closed the switch, it started charging the capacitor, but we use the same equation to see that it's actually not anymore decaying exponential, but it is growing exponential. One more thing I want to address in this equation, that if, let's say, your initial condition was not that, you are not saying that t is equals to, at t is equals to 0, your VC is not equals to 0, but let's say, according to your hypothetical initial condition, you're at t is equals to 0, your VC is not equals to 0, let's say, but your VC is equal to some voltage. Your VC is equal to V naught. There may be some voltage across the capacitor. Then you at t is equals to 0, in this equation, you will write something like this. V naught is equal to Vs plus K2 E minus 0, right? And then your K2 will become V naught minus Vs. So when you replace it in this equation, you will write it Vs plus V naught minus Vs K2 E minus T by RC, right? So this means that no, not K2 here. Right? So this means that you will then have the effect of V naught in it, okay? So this would, as this is another number, so it will not have any effect, but I'm just telling that it can be possible that you will not have initial condition as 0, but some voltage across it. So that's how you can incorporate that in your solution. Sounds good?
Sounds good.
Okay. Okay. So I will quickly go through now the inductor, so that if we have the similar situation for inductor, as we have said that we will talk about current through the inductor. So for the similar situation, we will write a KVL equation at t is greater than 0, right? So the KVL equation will be minus Vs plus Ri of t plus LdI by dt, because we know that VL of t is LdI by dt is equals to 0. Or I can just write it here as and replace it here. Minus Vs plus Ri of t plus Ldi by dt. Okay. So if you write this thing here, and now you will again form it in this form. Right? So in this form, if you compare it with what is your A here?
R over L.
R by L, right? Which means that your 1 by tau is R by L, right?
Professor, should it be VS over L?
Yes, 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 yes. Here there is something. Here it should be, if I, it should be, 1 minute. So this is by L. Right. Yes, yes, that's fine. Okay. Because I divided L by a whole equation, but I did not divide R by whole equation, right? Okay, so what I was saying is that my 1 by tau is R by L, right? Sounds good?
Yeah.
Okay, now if I replace this thing here as, so the equation was x by right? So if I replace this here, that will become I of t k1 plus k2 e minus t by tau, where I know that I should be writing it R by LT, but okay. Okay, sounds good. So let's replace this here. Can you see my screen?
Yeah, we can see it
It's,
now.
yeah, it's back.
Can you see the screen? Okay.
Yes.
Okay, sorry about that. 1 minute. So this will become K2 by tau minus E minus T by tau plus R by L K1 plus K2 R by L E minus T by tau is equals to Vs. So at T is equals to infinity, this will become R by L K1 is equals to Vs by L, right? So this will become K1 is equals to Vs by R. Sounds good? So replacing the value of K1 in equation of I of t, this will become I of t plus, I of t is equals to Vs by R plus K2 E minus T by tau, or you can also write Vs by R plus K2 E minus R by LT, right? Can you listen to me?
Yeah.
We can hear you.
Okay, so this is fine.
So far, yeah.
Okay, so let's try to apply initial condition. Apply initial condition to find K2. So the initial condition, we know t is equals to 0. At t is equals to 0, we have, let's say, IL is equals to 0. Then it will become 0 is equals to Vs by R plus K2. And this will become K2 minus Vs by R. And if I just write it here, I of t, Vs by R minus Vs by R, E minus R by L t. So that's how I know the current across inductor. But you know that this current is also a charging current if I plot it. So that's how we know that. That's why we can see this form of current. So this will be Vs by R, 0, and this will be current plot with respect to time. Okay, so if you pay a little bit more attention, you know that what we have done, we need three things here. We need to know, we need to find K1, K2, and tau, right? So for finding K1, I used steady state condition. And for finding K2, I used initial condition, right? So that's what I have done. But I will solve another problem to show one more thing. So right now, we just saw that there is t is equals to 0, but there is something more to it. But for the procedure, we need to know K1, K2, and tau. Sounds good?
Yeah.
Okay, so let me quickly solve another equation or another example so that it will be more clear what we are trying to do. Example 7.1. So in this example, we are given the circuit, something like this. So this is 6 kilo ohms. This is 100 microfarad. This is 3 kilo ohms, and this is 12 volts. We have this wire here, which says that at t is equals to 0, this switch will move to this wire, okay? So, which means that before t is equals to 0, it was like that. So now one thing I want to define, there we normally define it is as this: t is equals to 0 minus, t is equals to 0 plus. 0 minus means instant before change, and t is equals to 0 plus instant after change, right? So it means that just before switch was moving from position 1 to position 2, what was happening, okay? So that's what we call it, something like this. So you know that at t is equals to 0 minus, capacitor was being charged by the voltage source. So we think that capacitor is fully charged, right? And when it's fully charged, it conducts no current and acts as open circuit. So at t is equals to 0 minus, when this was the setup, before switch was moving from 1 to 2, we will draw another circuit. In this circuit, capacitor was fully charged, and this was the circuit at t is equals to 0 minus, right?
Right.
So we need to find what is VC 0 minus, right? So VC 0 minus will be, that's not difficult to find, because you can see that VC 0 minus will be the voltage across 3 kilo ohms. So we will write it as 3 by 9 into 12. So this will become 4 volts. So VC 0 minus was 4 volts, and that gives us the initial condition, which is just before the change in the switch happened. Now we we've used the information which is just before t is equals to 0. Now we want to, so the question was that you need to calculate I of t for t is greater than 0. So we will see that too. Okay, so we just found the initial condition, but now we know that at t is equals to 0, switch was moved from one position to 2. So I will write it like that. It's greater than 0. The circuit will be as shown, and KCL equation we will write, okay? So first I will draw the circuit. So when the switch moved, right? Now this is the new circuit. after switch moved. So this voltage source is out of the circuit now at t is greater than 0. So if we write nodal equation at this point, considering this as v of t, right? So I will write it something like this. V of t, let's say I just say that this is R1 and this is R2. Okay. So I will write V of t by R1 plus V of t by R2 plus the current C dV by dt is equals to 0. So now if I replace this and in a form of differential equation, which I, find familiar, I will write it like this. Sounds good?
Yep, sounds good.
Right? So that makes, if I compare this, this would be my A, right? So my A, I can calculate this A as by the given values. And I think it should be this. So my A will be 1 by 5, that is 0.2. This would be 1 by tau, or right. Yes. No. I'm wrong here. 1 minute. A is actually 5, right? A is actually 5, making my tau equals 1 by 5. So A is actually 5 is equals to 1 by tau, and tau is equals to 0.2. Okay, sounds good? Okay. Okay, now tell me that what is my solution here? Because I do not have any forced response here, right? So what would be my solution here? What should I write here? So my solution is normally, general solution is this, right?
Right.
But this solution is the solution that comes from forced response. That comes from if I have something like this, or something forced response here, which I am not having it here. So my solution should be only this, okay, for homogeneous equation. Okay, so what is there that I need to find it here?
Need to find K2.
Yes, I need to only find K2 here. So I can just write it like this. And can you see here, how can I find K2?
V of t equals 4 at t equals 0, right?
Yes, so I need to put initial condition, right? To find K2. Which was 4 volts. And because the capacitor voltage cannot change instantaneously, that's why we are saying VC0 minus is equal to VC0 plus is equals to 4 volts. So at t is equals to 0, I will write it as 4 K2, right? And this would be 1. So this K2 is equals to 4. So my V of t is equals to 4e minus t by 0.2. But that's not what we need to find. We need to find I of t, right? So I of t is what? Okay, 1 minute. So they have defined here, I think I did not. So this is your I of t. In this branch, so your I of t is P of t by R2, which will be 4 by 3 E minus t 0.2 milliamps. Sounds good?
Yep.
Okay, so so I am just writing the step by step what we have defined. I'm just summarizing it, that what is the step by step approach for this analysis technique. And then I am leaving some parts of this chapter to move to second order circuits. And when I will give you homework, you will know that which parts we have not included. So that's some step-by-step summary of this analysis technique. So I'm just quickly summarizing it. Step number 1. Solve for initial condition. That is VC0 minus or IL0 minus, depending on type of problem. Step number 2. Define first order differential equation in terms of state variable VC of t or IL of t. So you need to define it something like that. It comes like this so that it will be easy for solve. VC of t in case of RC circuit and IL of t in case of RL circuit. Okay. So step number 3. Step number 3 is put above equation and form in this form, okay? So the equation you need to put is dx by dt plus ax by of t is equals to f of t. It can happen that you don't have f of t, then you are having only solution of natural response. Okay. So note that our general solution is x of t is equals to k1 plus k2 e minus t by tau. Okay. And then find k1, k2, and tau, right? So find k2 using initial condition, k1 using steady state condition, and tau by comparing with A. Sounds good?
Yes.
Okay, so these are pretty much our steps for this technique. Okay, we have a little bit time left, so I'm just quickly introduce second order circuit, which we will be doing next time. But so we are good with this first order circuit. You know what is the first order circuit? The first order circuit, one thing you have learned maybe in calculus, that first order circuit. Can you hear me?
Yeah.
Yeah.
So the first order circuit is the circuit in which you have a linear equation or a first order differential equation, right? That's what you have learned. But in the circuits, first order circuit is just not only that in which you have first order differential equation, but the first order circuit is in which you have one storage element, like either you have capacitor or you have inductor. So what I can say that, so we were doing first order circuits. So first order circuits are circuits which comprises of one storage element, either capacitor or inductor. So automatically, you know what is your second order circuit. So in terms of calculus, second order circuit is in which you have second order differential equation. But for circuits, it is that which has two storage elements. That which are inductor and capacitor. So let's examine two types of second order circuits. So if this is IS, this is IR, this is IL, this is IC. Similarly, if this is VS, This is VR. This is IL or VL, and this is VC. So these two types of second order circuits we will learn. So this is called parallel RLC circuit, and this is called series RLC circuit. So if I just write the equation of parallel RLC circuit, I will of course use KCL equation, and that will be IS of t is equals to IR of t plus IL of t plus IC of t, which is VC by R. Okay, so now this whole node is same. So here it could be V of t, and they are saying VC of t, it doesn't matter because this is the same thing. So you are saying VC by R plus, I will write this as, I will leave this thing as IL by T of T plus C dVC by dt. Now this thing is actually equal to 1 by L 0 T VC of T dt plus initial condition. Sounds good? Can you hear me?
Yes. Okay.
Okay, okay. So if I write this equation, which is, this is KCL equation, and this would be KVL equation. Then I will write it as Vs of t is equal to VR of t plus VC of t plus VL of t. So like here we have defined VC of t, here we will define IL of t. So it just, the same current is flowing in all the elements. So I'm just writing it as this IL of TR plus VC of t, I will write it as it is, and this will be LDIL of t by dt. Now this thing can be written as VC of t plus is equal to 1 by C 0 of t IL of t dt plus initial voltage. Okay, sounds good?
Yep. Sounds good.
Okay, so I think we will stop it here, and I will upload the remaining lectures, and today I will post chapter number 8 homework. Okay,
Okay.
thank you very much for today's lecture. Thank you. Bye.
Thank you. Have a good day.
Bye.
Thank you.